Let's find the coordinate of each critical point. We're going to find a coordinate. It's going to be an x and a y value. Critical points occur where the derivative equals 0 or where the derivative doesn't exist. This is not a function. You could graph this on Desmos or some sort of online graphing utility that will graph non-functions, and you'll see it looks like a function, except actually at one point, from what we can see, it has some odd nuances to it. So we want to find the coordinate of each critical point. Let's start by taking the derivative, and that will, of course, involve implicit differentiation. Sorry, that marker did that thing again. 3y squared dy dx minus 2y dy dx equals 2x. Okay, solve it for dy dx. We're going to factor the dy over dx out. Notice sometimes it's called dy dx, and sometimes just in a hurry you might call it dy dx. dy over dx, dy dx. It's just, you know, matter of hurriedness as you speak it. So 3y squared minus 2y. 2x, there we go. We're going to factor the dy over dx out. They were all on the same side anyway. And then we'll divide by this. So dy over dx equals 2x over 3y squared minus 2y. Yay! Good to know. Fantastic. So here's the deal. We need to know everywhere that this equals 0 or everywhere that it doesn't exist. So we're going to find all the coordinates and our answers. They'll go over here in this space. I'll probably put some work here. Probably should have backed all that up over here, but I'm not able to click and drag it. So here it goes. Work will go here. Answers will go here. It's going to be a little bit out of order, but we'll deal with it. So I want this to equal 0. I can go ahead and put that there. And if this is going to equal 0, then x equals 0, right? X equals 0. So we're going to say, well, all right, let me say that differently. If a fraction equals 0, it's the numerator that equals 0. So 2x equals 0, so x equals 0. So x equals 0 is a possibility for an answer, and what I'm going to do is write that down as a final answer. My answer is going to be 0 comma something. I might get more than one something out of that. We'll see. Let's just kind of tinker with this. So answers are going over here. We have x equals 0 as a possibility for the start of an answer, and we're going to explore that. So if x was equal to 0, we'll bring my work over here. What color? Let's stick with blue. If I was to say, well, x equals 0, I wonder what the y coordinate is that goes with that. So we would say, well, y cubed minus y squared equals, well, 0 squared. I'm plugging in 0 right there. So y squared, y minus 1 equals 0. So y squared equals 0, y minus 1 equals 0. A lot of this can happen in your head. Y equals 0 and y equals 1. Yes, okay. Here's what just happened. We found where the derivative equals 0 by finding the derivative, setting this fraction equal to 0, saying, hey, if my fraction equals 0, my numerator is 0, so x is 0. Well, that's great. I need to know what y value or y values correspond to that so I can finish writing my answer. There's more than one. 0, 0 is an answer. 0, 1 is an answer. Don't get carried away with that. We have some correcting to do, by the way. We're going to tinker with that in a minute. So critical points occur where the derivative equals 0, mission accomplished, and where the derivative does not exist. So we also have to consider where the derivative doesn't exist, and that would be where the denominator equals 0. So we're going to consider that as well. Before I go there, let's mark out one of those answers. Why? Okay, this is tricky. Whenever you're in a situation like this, and I say situation like this where I've seen this a lot on these type of implicit differentiation problems. Implicit differentiation has so many nuances to it. They may say, find a coordinate that satisfies blah, 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 blah. Well, 0, 0 is part of this graph. 0, 1 is part of this graph. But there's something really tricky about one of these. And I want to show you what it is and just kind of get your antennas up, so to speak, if that's a thing, so you can start looking for that. If I plugged in 0, 1 into this, it would work. Not an issue. If I plug in 0, 1 into this derivative right here, it would work. Not an issue. 0, 1 is fine. He will live. Good for you. If I plug 0, 0 into the original, I almost called it function, not a function, then I would have something that checks out. If I plug 0, 0 into the derivative, I have 0 in the numerator, 0 in the denominator, and you just did 0 divided by 0. And so because this one is indeterminate, remember 0 over 0 is like not allowed for lots of reasons. So indeterminate. Now if we're dealing with the limit at an indeterminate form, we use L'Hopital's rule. This is not a limit, we're not doing that. So this is indeterminate, that is not even an answer, okay? And we still haven't found all the possibilities. Maybe we have. Let's keep exploring. This is fun. All right, I'm going to erase this work now that I've been standing in the way for the longest time and you can't see it. Pause the video if you need to, but probably already got that copied. I also need to consider where the derivative equals 0, check, where the derivative doesn't exist, and that would be where the denominator equals 0. Okay, what I am considering right now is where my derivative would not exist, which would be the things that make my derivative not exist, like dividing by 0, right? So we are going to set this equal to 0. Sorry for the clicking. It's bumping up against a button. Microphone's bumping against a button. There we go. Crisis averted. Why is it bumping against a button? Because I said so. So y equals 0 is a possibility, and 3y minus 2 is a possibility. So y equals 2/3 and y equals 0. Okay, well, let's just be real honest with ourselves. If y equaled 0, we'd plug in 0, we'd get 0, we've crossed that bridge, we've burned that bridge, we done. Okay, I'm looking for everywhere that the derivative equals 0, check. Everywhere the derivative does not exist, working on it now. That one's not a possibility. We burned that bridge a long time ago. But I do need to consider, maybe, just maybe, that y equals 2/3 is an answer. I'm going to walk over here and pretend like it's going to work. Ooh, was that foreshadowing? I think I just told you it's not going to work. If you're like, I don't know if I should write that or not. Don't waste your time. But here's why it's not. I'm gonna figure out some stuff. If y equaled 2/3, that'd be great, but I want to know what x would be. Like, I need a coordinate, right? So I'm going to take that 2/3 and I'm going to plug it in. I'm going to figure this out. So I'm going to plug it in right up there. So 2/3 cubed minus 2/3 squared. Whoa, what in the world? When your parenthesis becomes a squared. Should make a meme out of that. Okay, so 2/3 cubed minus 2/3 squared equals x squared. And I'm left with 8 over 27, cube the top, cube the bottom, sorry, cube the numerator, cube the denominator. Let's use proper vocabulary here. 4/9 equals x squared. We'll get a common denominator, that would be 27. 8 over 27 minus 27 times 4, 12, and there's x squared. Negative 4 over 27 equals x squared. All right, we've hit a problem. In this class, we don't play with imaginary numbers. Wish we did. So much fun. Calculus, imaginary numbers, it's like Candyland for math teachers. But we have x squared equals a negative number, so we're going to have to, excuse me, I thought I had to sneeze there. Like, we're going to have to take the square root of both sides. As we take the square root of this, square root of this, we realize we're taking the square root of a negative number. So we just played with imaginary numbers. No, not in this class. So we didn't even finish this one, but no. This is the only point, critical point, x and y value, the coordinate, that is, well, a critical point for this equation that is not a function.